An elliptic curve is a very delicate and important object that subtly twists through the plane. The gentle turns that grace these curves arise from the cubic Diophantine equations that describe them. In the previous lecture, we found rational points on a circle by studying intersections with certain lines. Here, we'll extend this theme to see that the rational points on elliptic curves enjoy an incredibly rich arithmetic and geometric structure. This structure, which only comes into focus by studying the intersections of these elliptic curves and lines, is now understood through some very recent, remarkable 20th century advances due to Louis Mordell, Barry Mazur, and others. We'll describe some of these results and mention a few open questions that continue to intrigue number theorists and geometers across the globe today. We'll also see how these elliptic curves are, in actuality, level curves or contour lines of a three-dimensional surface. Just as we might read topographic maps to better understand the terrain on a certain mountain range, here we'll study these elliptic curves and realize that they can be viewed as contour curves describing the surface, of all things, of a doughnut. Well, this delicious insight leads to many important theorems and conjectures. We'll close this lecture by turning to one of the most significant applications of these ideas, the dramatic conclusion of the story of Fermat's last theorem. Well, in the previous two lectures, we focused on the Pythagorean equation, an equation that contains exponents of 2 and therefore is known as a quadratic equation. Now, in the last lecture, we exploited the important insight that natural number solutions to the Pythagorean equation correspond to rational points on the unit circle. Here, we'll take these insights and apply them to more complex and thus more interesting objects. In particular, here we'll study certain Diophantine equations that contain the exponents 2 and 3. These are special classes of what are called cubic equations. Now, the equations that we'll consider all have the general form y squared equals x cubed plus a times x plus b for fixed given integers a and b. So, for example, we'll study y squared equals x cubed minus x, and also y squared equals x cubed minus x plus 1. These equations describe curves that can be graphed in the coordinate plane, just as we graph the unit circle and other conic sections. The curves associated with these cubic equations are called elliptic curves. So the graphs representing the equations y squared equals x cubed minus x and y squared equals x cubed minus x plus 1, those graphs are each examples of elliptic curves. So, but before moving on, let me just say a word about the origins of the phrase elliptic curve. Because if you look at these images, you'll notice that these curves are certainly not ellipses. So where'd they come from? Well, returning to the circle for a moment, we recall that if we want to determine the length of the circle, in other words, its perimeter, or better known as its circumference, then we can apply the ancient famous formula that circumference equals 2 times pi times r, where r represents the radius of the circle. Well, the length of a curve is called the arc length. So the formula for the arc length of a circle is well known. On the other hand, it's much more difficult to compute the arc length of ellipses, those special oval conic sections that we saw from the previous lecture. Now, those computations to find the arc length involve complicated objects known as elliptic integrals from calculus. Associated with these elliptic integrals are functions later known as elliptic functions. These functions are, in fact, connected with the equations of the form y squared equals x cubed plus a times x plus b. And that's why we call such expressions today elliptic curves. The study of elliptic curves really began in the 19th century, and the important initial contributions to the field were made by the Norwegian mathematician Niels Abel, the German mathematicians Carl Jacobi and Carl Weierstrass, along with Gauss and Legendre, of course. They're basically doing everything. They're always running around, giving important mathematical insights. If x and y are two numbers that satisfy the equation for an elliptic curve, then the point x comma y is a point on the graph of that elliptic curve. Moreover, if x and y are each rational points, then we say that x comma y is a rational point on the elliptic curve. Now, just as with our exploration into the unit circle, here we wish to find rational points on elliptic curves. Let's recall that the highest exponent in the equation for an elliptic curve is 3. It's a cubic. So because the highest power is 3, if we intersect its graph, its elliptic curve, with any straight line, then there will be up to 3 points of intersection. For example, let's consider the intersection of the elliptic curve y squared equals x cubed minus x with the line y equals x. That's the line that kind of cuts through right at a 45-degree angle. So that's the kind of like a diagonal line, if you will, that passes through the origin 0, 0. Well, if we solve these equations simultaneously, we'd see that x squared equals x cubed minus x, because I replaced the y by x in the elliptic curve, which gives us, if we bring everything over to one side, x cubed minus x squared minus x equals 0. We could factor out a common factor of x and see x times x squared minus x minus 1 equals 0. Now, we have a product equals 0, so either the first term is 0, which means x equals 0, or the second factor is 0, x squared minus x minus 1 equals 0. However, we've actually already found the solutions to the second equation in lectures 5 and 6, namely x equals 1 plus or minus the square root of 5 all divided by 2, namely the golden ratio and its conjugate. So we see 3 points of intersection as advertised. Now, finding the y values in this case is easy, since these points are all on the line y equals x. In other words, x and y have the same value. So we actually found the 3 points of intersection of this cubic equation, this cubic elliptic curve, I should say, and this line, namely 0, 0, and then the golden ratio, comma, itself, and the conjugate, 1 minus square root of 5 over 2, comma, itself. 3 points of intersection. Well, it's a theorem from high school algebra that if a cubic equation having integer coefficients has 2 of its solutions equal to rational numbers, then its third solution must be a rational number as well. And to illustrate this fact, let's consider the cubic equation x cubed minus 4x equals 0. Now, we can check that 2 of its solutions are in fact rational. I claim one is x equals 0 and one is x equals 2. Let's check it. If we let x equals 0, then we see 0 cubed minus 4 times 0, which is 0, which equals 0. Good. What about when x equals 2? Well, 2 cubed is 2 times 2 times 2. That's 8. Minus 4 times 2, that's 8. 8 minus 8 is 0. So both, in fact, are solutions. We found 2 rational solutions. Therefore, the third solution must be rational as well. And indeed, it is. The third solution is x equals negative 2. Now, we can also find these solutions for ourselves by factoring the equation. X cubed minus 4x, I could factor out the x and see x times x squared minus 4, and that can be factored into x times x minus 2 times x plus 2 equals 0, and then we see either x equals 0, x equals 2, or x equals minus 2, as we found earlier. Well, This theorem holds an extremely important implication within the world of elliptic curves. Suppose that we find two different rational points on an elliptic curve. If we connect those points with a straight line, then the line will intersect the elliptic curve at a third point, since remember that we have a third-degree equation. The theorem we just mentioned implies that the third point of intersection must be a rational point as well. So, if we have two rational points on an elliptic curve, we can generate a third rational point. Simply connect those two rational points with a straight line, and the third point of intersection must be another rational point. Well, but we now notice that if we look at the graph of any elliptic curve and reflect its image over the horizontal x-axis, then in fact the curve lands exactly back on itself. Namely, if we look through the x-axis, we see the mirror image of the curve above and below that axis, as if the x-axis was the surface of a lake devoid of any ripples. We'd see that reflection. We say that the curve is symmetric, or more precisely, symmetric about the x-axis. It has this symmetry. Moreover, if the point x comma y is a rational point on the elliptic curve, then its reflection, which would be x comma negative y, is also a rational point on the elliptic curve. Now, we can now pull all of these observations together and discover that the rational points on elliptic curves can be connected with each other through a new type of arithmetic, one in which we can, in some sense, add, if you will, two rational points on an elliptic curve to yield yet another rational point. And we call this operation addition, but it's not at all connected with the usual addition of numbers that we've been using since we can remember. Let's now see how this strange type of addition is performed in practice. It's a little strange, so let me just warn you right up front. To add two rational points on an elliptic curve, we first connect them with a straight line. And then we look at the third point of intersection of this line with the curve. And then what we do is, now we know that third point is a point of intersection, which is going to be another rational point on the elliptic curve. Now, a great guess would be that this third point would be the sum of these two numbers. However, it turns out that that natural sounding definition would not reveal any arithmetic or algebraic structure. So instead, we perform one more step in order to define the sum. We now consider that third point's reflection around the horizontal x-axis. And this gives us yet another rational point down here on the elliptic curve, and it is this point that we call the so-called sum of the first 2 points. Take the 2 points, connect them, goes to a rational point, reflect it down, that point is the sum. In other words, this peculiar addition is defined geometrically by studying the intersection of a line and a curve. We call it addition because under this operation that combines two rational points to produce a third one, the rational points on an elliptic curve enjoy all of the basic properties that the integers enjoy under usual addition. The operation is associative, doesn't matter which way you add. There's an identity element, in other words, there's a version of 0, and every element has an additive inverse. Now, by the way, let me just say that the associative property that you can add these two first and then add the next one, or add these two and then add the first one, that's actually the most challenging to verify. And the identity element, the kind of 0, is a little strange, and I'll hint at it in a moment or two. Well, a collection of objects that has an operation that satisfies all these properties is called a group. And it's an abstract algebraic structure. Now, the area of abstract algebra known as group theory has its focus on identifying the different types of possible groups we can have. So the rational points on an elliptic curve in fancy language form a group under this unusual addition. In 1921, the British mathematician Louis Mordell was able to classify what types of groups these collections of rational points could be. His result shows, among many other deeper consequences, that all the points on an elliptic curve, whether there are finitely many points on the curve or infinitely many points, because there could be either, can be found by successive so-called additions of only finitely many rational points. Now, such groups are called finitely generated groups. So what that means is, if you want to get every single rational point on a particular elliptic curve, you only need finitely many points to be identified, and then just keep adding them to themselves and to each other. And if you keep doing that, you'll actually generate all the rational points on the elliptic curve, whether there are only finitely many rational points, which could happen, or infinitely many rational points. You can get them by just generating from a finite collection of points additions. In other words, it's a finitely generated group. Well, in 1977, Barry Mazur from Harvard University proved an amazing theorem that in some sense quantifies Mordell's theorem. Among other things, Mazur showed that if an elliptic curve contained only finitely many rational points, then it can have no more than 16 of them. Isn't that amazing? No matter what the elliptic curve is, if we know there are only finitely many points, there can't be any more than 16. So if you did some kind of result with some elliptic curve and you concluded that you've got at most 1,000 points, you automatically know that you have no more than 16. Okay, let's momentarily return to the circle and ask, what if the circle were a slice or a contour curve of some simple three-dimensional surface? What could we visualize that surface to be? So think of a circle not as a flat thing now, but as a level curve of some object. Well, a sphere, it would be a great answer, because if you slice a sphere, take it off, what we'd actually see would be the boundary of a circle. And so this represents the level curve of a sphere. That's what a circle is. So that makes sense. That makes sense? All right? It's all right. Okay, good. So, senior Wences. Okay, well, let's now consider elliptic curves. For example, let's look at y squared equals x cubed minus x. Now notice that as the curve moves to the right, the top wing is rising up vertically without bound, while the bottom wing is actually falling down vertically without bound. Now, this next step will seem a little bit wild at first, because we're going to try to now imagine this curve not on a flat plane, but instead on the surface of a sphere, on the surface of a ball. Now, in this surface, these wings that are initially heading in opposite directions will eventually approach each other. And in fact, those two wings would actually meet. Now, this is a very, very unusual thing, and I want to say a word about how to visualize this. So imagine, instead of considering the elliptic curve on a flat plane, we consider it on a balloon. So take a balloon, inflate it. Okay, so there's a balloon. How do we put the elliptic curve on the balloon? Well, what we do is, imagine I could put my fingers inside the balloon and stretch out the air hole. If I stretched out the air hole, and if it wouldn't rip, I would finally get a huge orange disc. In fact, I would see this. This is, in fact, the balloon stretched out, where the air hole is now way over here. Let's now graph an elliptic curve on here. This is going to be my own little version of it, so don't take me literally. So here's my attempt to draw an elliptic curve. So that's not too bad. And of course, this is going to go on for forever. So if this goes on forever, and this goes on forever, these two wings go on forever, well, what do we see? Well, if we now pull this back and make this back into a balloon, well, this is all the air holes. So these are going to meet up. And in particular, if we did this, what we would see is this. This little piece right here is the wing right here. And then this part that goes through the air hole is precisely given by this. Notice how this goes back up to the air hole, and they want to touch. So in this case, what we see here is something interesting. First of all, the name of this, where we take the plane and put it on a balloon, this actually is known as stereographic projection. Now, with this strange vantage point, our elliptic curve now appears to be two closed loops. Do you see it? One closed loop is here, and the other closed loop is here. Now, if we think of that as being a level curve of something, what familiar object is that a level curve of? Well, in fact, you might be eating these every morning. It would be the level curve of a bagel or a donut. If you take a bagel or donut and slice it, notice what you see are indeed two closed loops. Two closed loops. In mathematics, we actually call this a torus. So the surface of a donut or the surface of a bagel is called a torus, and when we cut it open, we'd see those two closed loops. Now, notice that the second circle comes from, notice that the circle, the original circle that we looked at here, comes from a second degree equation and represents a slice of a hollow sphere, a three-dimensional surface with no holes. While the elliptic curve comes from a third degree equation and represents a slice of the surface of a donut or bagel, a three-dimensional surface that has exactly one hole. Well, it turns out that the graph of the corresponding fourth degree equation could be viewed as a slice of a three-holed donut, if you could imagine such a tasty vision. But actually, you don't have to imagine it, because I happen to have one here. Here is an example of a three-holed donut. And if you think I'm joking, I'll hold it right up for you. There it is. There's a three-holed donut. And if you slice this, in fact, what you would see would be the level curve of a fourth degree equation. And in general, the higher degree an equation has, the more holes its associated surface has. Well, we saw in the previous lecture that the unit circle, which we can now view as a curve of a zero-holed sphere, contains infinitely many rational points. We found that for ourselves. Here in this lecture, we remarked that some elliptic curves, which result in slicing a one-holed donut, could have infinitely many rational points, while others would have only finitely many rational points. Mordell in 1923 conjectured that for all curves representing slices of surfaces having more than one hole, such as the three-holed donut, those curves contain only finitely many rational points in the coordinate plane. In 1983, the German mathematician Gerd Faltings proved that Mordell's conjecture is indeed true. 3 years later, Faltings was awarded the Fields Medal, the equivalent of the Nobel Prize in mathematics, for his groundbreaking work. So, elliptic curves, those special curves of degree 3, are the most enigmatic curves in the following sense. In the simpler, lower degree cases, such as the circle, those curves always contain infinitely many rational points. In the higher degree cases, such as degree 4 or higher, Faltings' proof of Mordell's conjecture shows that these curves contain only finitely many rational points. But the elliptic curves having degree 3 can contain either infinitely many or finitely many rational points. Hidden within this delicate structure of elliptic curves turns out to be the solution to Fermat's last theorem. And we're now ready to face its dramatic conclusion. In the late 1960s, French mathematician Yves Elegouache had an interesting idea. He dared to assume that for some odd prime number p, there actually was a natural number solution to the Fermat equation a to the p plus b to the p equals c to the p. In other words, he assumed Fermat's last theorem was false. There was a solution. Remember, Fermat's last theorem said there wasn't. He then used these numbers to create an elliptic curve. In particular, the elliptic curve y squared equals x times x minus a to the p times x minus b to the p. Well, this elliptic curve would possess some very unusual properties owing to the fact that the sum of the numbers a to the p and b to the p is yet another perfect power of p, namely c to the p. Years later, German mathematician Gerhard Frey believed that such an elliptic curve would be so unusual that it would actually contradict an important conjecture about elliptic curves known as the Taniyama-Shimura-Weil conjecture. And everyone, by the way, believed this conjecture to be true, even though no one knew how to prove it. Well, in 1986, Ken Ribet of the University of California at Berkeley proved that indeed Frey was correct. The truth of a special case of the Taniyama-Shimura-Weil conjecture would contradict the assumption that there was a natural number solution to Fermat's equation. In other words, it would contradict the assumption that Fermat's last theorem was false. That is, Ribet proved that if a special case of the Taniyama-Shimura-Weil conjecture was true, then that would automatically imply the truth of Fermat's last theorem. Well, now we come to Andrew Wiles. Andrew Wiles is a British mathematician who, as a young boy, read in the mathematical story of Fermat's last theorem. And believe it or not, after reading the story, it became his childhood goal to find a proof. Well, in the intervening years, he actually earned a PhD in mathematics at Cambridge and then moved to Princeton, where he's now a professor and producing very important work in number theory. Well, once Wiles heard of Ribet's important result from the 1980s, Wiles decided to work full-time on proving that special case of the Taniyama-Shimura-Weil conjecture. And in fact, he worked in total secrecy for 7 years. Finally, in June of 1993, at a conference held at the Isaac Newton Institute for Mathematical Sciences in England, he delivered a series of 3 lectures, culminating with a proof of the Taniyama-Shimura-Weil conjecture, and thus producing a proof of Fermat's last theorem. Now, let me say a word about this. No one knew that he was going to do this, and so people were sensing it. As these lectures went on, they were sensing he's going to do something big, and the news started to spread through email. Now, at that exact same summer of 1993, I was actually attending a conference in Hungary in honor of Erdős's 80th birthday. And you might remember from a previous lecture, I was talking about how Atle Selberg was at this conference, and Selberg and Erdős had this big feud, and they weren't talking to each other, and they were finally reconciling. And we all thought in Hungary at that time, we were at the center of the excitement of mathematics. Little did we know that just up the road in England, Wiles was announcing the proof of Fermat's last theorem, and of course, he trumped everybody. Well, unfortunately, during the peer reviewing process of the work, an error was uncovered. Happily, however, in September of 1994, a complete and correct proof was in hand, and Wiles fulfilled his childhood dream. Fermat's last theorem was finally a genuine theorem. Today, algebraic geometers continue to uncover new findings about elliptic curves. There are many, obviously, open questions that remain, questions that generalize Fermat's last theorem in a variety of different directions. One such question is known as the ABC conjecture, which roughly states that if we have 3 natural numbers, A, B, and C, sharing no common prime factors, and for which A plus B equals C, then C is not too big in terms of the product of all distinct prime factors of A, B, and C. Yeah, it's a little bit cryptic, but that's the idea. Now, a proof of this result would immediately imply Fermat's last theorem, thus giving us a second proof, if you will, of Fermat's last theorem, and would even also prove Mordel's conjecture, which Faltings proved back, and would also prove the twin prime conjecture, which still remains open, a great question about primes that we saw earlier. The arithmetic of rational points on elliptic curves has implications within the context of factoring large numbers into primes, and thus the arithmetic of elliptic curves is also important and has serious implications for the modern practical world of cryptography. Elliptic curves, a beautiful notion that pulls together ideas from geometry, Diophantine analysis, the primes, and finally gives us an answer to the age-old question of Fermat's last theorem. a beautiful area that brings together all these wonderful sights and sounds of mathematics.